The first speaker of today is Dominique Bourne, and we speak about congruence modular variety, GUM category, and algebraic crystallography. Please refrain to make questions during the talk. You will have some minutes at the end of the talk to ask a question and do your comments. Thank you very much. And now I leave Dominique the stage, please.
Thank you very much, Beppe. And thank you to all the organizers for what seems to be really a new Herculean work. So, and thank you to the scientific committee to give me the opportunity to speak at this CT 2021. So, in 1983, GUM characterized the congruence modular variety by the validity of the shifting lemma. Doing this, it translated the usual modular formula for congruences into geometric terms, following which, given any triple of congruences satisfying this inclusion, then the existence of the solid arrows determined the existence of the dotted one. And of course, the main interest of the shifting lemma is that it is freed of any inductive condition. So, by the Yoneda embedding, the shifting condition has the meaning in any category E. And first, a very simple categorical characterization of this condition in a finitely complete category was described by Marino Guan and myself. And in this work, the first consequences of this categorical shifting property were investigated, mainly concerning the centralization of equivalence relation, the internal groupoids, and the internal category. Later on, later on, we call GUM category the category satisfying this categorical shifting lemma. As a result, I denote by PTA the category whose objects are the split epimorphism, and with a given splitting, on morphism, the commutative square between them. By this symbol, I denote the functor associating its codomain with any split epimorphism. It is a left exact fibration whose Cartesian map are the pullback, and it is called the fibration of point. And of course, it has a very important classification power in algebra. I shall only recall the following one. A category E is a Malsev category in the sense of carbonyl Lambek-Pedicchio, if and only if any fiber of this fibration is unital. And the category E is naturally Malsev in the sense of Johnston, if and only if any fiber is additive. Now, in the same way, the GUM categories can be characterized also by this fibration. And here is the characterization theorem. The category is a GUM category if and only if the fiber of the fibration has any of these three conditions. I shall have only time to develop the condition 2. And so what is a congruence hyperextensible category? It is a punctured category. And we shall need to define the notion of punctual span. A punctual span is nothing but a commutative square or split epimorphism above the zero object. And of course, when the category is punctured, and with this notion, the shifting lemma can be desymmetrized. And so I called congruence hyperextensible, or CH for short, a punctured category, such that given any equivalence relation T on W, which contain the intersection of the kernel equivalence relation, then the existence of the dotted arrow is a consequence of the existence of the solid one. And I call it hyperextensive because this diagram shows that some information about T on the subcategory Z can be extended to the whole object W. So any Johnson-Tarky variety, as the category MON in particular, is CH. Any regular unital category is CH. And so by this last example and the characterization theorem, we get immediately that any regular Mal'Shev category is a GUM1. Of course, all the results I shall explain for GUM categories will be valid in the Mal'Shev context, but several of these results were not yet known in the Mal'Shev context. So some results for GUM category are new considering the Mal'Shev categories. Here is an example which is not unital. It is a punctured variety with 3 ternary operations satisfying this list of axioms. And I determine this very curious example a priori by using the characterization of GUM of the congruence modular category and putting some 0 at some place. A first meaningful result is the following. Given any CH category, consider a punctual relation, not any punctual span, but a punctual relation, then PZ is necessarily the co-kernel of the zeromorphism here. And more unexpectedly, this PZ is a unique map from W to Z, which fulfill the equation of the punctual span. One interesting consequences of this first property is that in such a category, any subtraction D on an object X is necessarily the difference mapping of a group structure, which is then necessarily abelian. And moreover, on any object X, there is at most one subtraction. And naturally, any morphism, and naturally, any morphism between 2 objects equipped with a subtraction is a subtraction homomorphism. Just a sketch of the proof of the uniqueness of a subtraction. Any subtraction determines a punctual span. And as soon as you know that the subtraction is associated to a group structure, this subtraction is left cancelable. And so it determines a punctual relation. And according to the previous result, this D is unique. So this uniqueness property makes intrinsic the notion of internal abelian object in a CH category. Whence, of course, the following definition: an object is said to be abelian when it is endowed with this unique subtraction, and we denote by Abe E the full subcategory of abelian object in E, which is then additive and stable under finite limits. So what are the structural outcomes of this characterization theorem on the GUM categories? So since the GUM category is characterized by the fact that any fiber is CH, then any fibers is then the GUM category is canonically equipped with a specific class of split epimorphisms, namely those split epimorphisms which are abelian in this fiber. And according to the definition, this means that given any split epimorphism, it is equipped with a map from the kernel equivalence relation to X, satisfying, of course, the 2 axioms of a subtraction. And then necessarily, this formula determines an internal group structure on the object F in the size category, a group structure which has the morphism F as unit. We should denote by APTA the class of abelian split epimorphism, and this will provide us with a golden thread, which we are now going to follow in investigating the properties of a GUM category. So let us introduce the following definition. An equivalence relation will be in a GUM category will be said abelian when the split epimorphism D0 S0 is abelian. A morphism we will say to be APT special when its kernel equivalence relation is abelian, and then an object X is said to be affine when the terminal object is the terminal map is APT special. Translating this definition, an equivalence relation R is abelian if and only if there is a ternary operation on the related object such that P of A, R, B, R, C is in relation with A, P of E, R, E, R, B is B, and P, R, E, R, B, R, B is E. So you, of course, you recognize there the Maltsev condition. In particular, an affine object is nothing but an object equipped with a ternary operation satisfying the Maltsev identities, and then it is necessarily, this operation is necessarily autonomous. So this golden thread led us quasi immediately to some observation already made in my work with Marino Gran, but in the last paper, this last paper, they were obtained after a long combinatorial calculus on relation, and now they derive automatically from the characterization theorem and the fact that the CH category has an intrinsic abelian object. What are the properties of the abelian split epimorphism? Of course, they are the best possible properties. They are stable under pullback and stable under finite limit in PTE. And the second property is very important because this implies that the subcategory of APT special above Y is a naturally Maltsev category. In particular, that implies that the category of affine object is a naturally Maltsev category. And this naturally Maltsev property is important since when a GUM category is exact, you can construct the Bayer sum of APT special extension with a given direction. Of course, there are many other outcomes, but now we shall focus our attention on how the shifting lemma is related to the construction of the universal abelian split epimorphism. For that, let us introduce a basic construction. Given any map F, which we call diagonal punctuation of F, the push out of the reflexive part of the kernel equivalence relation along F. Of course, this is a push out. So the projection D0 determine a map here, which is again gives us a downward push out. And it is very easy to see because F co-equalizes the two projections, that the second projection determines the same CF, so that from this construction you get here a split epimorphism. And it is why I call it the diagonal, because you use the diagonal punctuation because you obtain a point. If you complete this diagonal punctuation by the kernel equivalence relation, of course, here you get a reflexive relation. And in any case, this relation is above Rf is symmetric because Rf is itself symmetric. And now, here is our main theorem for this talk. In a GUM category with diagonal extension, then this reflexive and symmetric relation is actually an equivalence relation. So that the result can be thought as a kind of Maltsev remainder inside the GUM categories. Some specific classes of reflexive and symmetric relation are actually equivalence relations. Now, coming back to the varietal case, we can show more than in any GUM category. We can show that when F is a split epimorphism, this split epimorphism, this downward square are not only push out, but regular push out, meaning that the factorization to the pullback is a regular EP, and this immediately allows to transfer the groupoid structure here to the groupoid structure to a groupoid structure here, so that the point here is canonically equipped with a group structure. In other words, this construction produces from F an abelian split epimorphism. The diagonal punctuation of a regular epimorphism gives us an abelian split epimorphism. And when F is split, this abelian split epimorphism is a universal one associated to this one. Of course, the question now is it possible to extend this observation to any GUM category? And of course, you guess that you need another axiom. I have no time to give the definition in detail, but when the category is a regular category, this condition, natural, is equivalent to the fact that any slice category is a factor permutable in the sense of Bourn. And it is very easy to see that it is true that any congruence category is of this kind. And this shows that, once again, congruence modular variety has another aspect of the Maltsev context. And now the main theorem is when E is a regular GUM category satisfying this axiom, then the construction I gave previously gives us the universal abelian split epimorphism associated to any split epimorphism. And of course, I already said that since any regular Maltsev category is a GUM1, all the results here can be extended to the regular Maltsev category, and many of them were not already known. So now the last step of my talk. We observe that in a CH category, there is an intrinsic notion of abelian object. We were already confronted to this uniqueness property in the unital and strongly unital categories. But in this context, it was not so surprising. Actually, I was not so surprised according to their varietal origin. Of course, this can be understood because in the varietal context, this happens because and when some term of the variety became homomorphism. But here, coming back to our non-unital CH varietal example, we can keep on accepting this uniqueness so easily. We have to think it as a surprising, or at least I have to think it as a surprising phenomenon. So let us denote by X the variety defined by the above terms and equation. The surprise can be made more explicit in the following terms. If it is natural to consider the category AB of abelian group as a full subcategory of the category mon of monoids, it is not so natural to think of AB as a full subcategory of X or of any CH variety. So beside the potential and not yet known positive interest of X algebra, this notion of X algebra appears now to be also interesting by what the whole variety X of this algebra is able to reveal through the environment it creates. More precisely, the variety X could be thought as a kind of photographic negative for the abelian group structure, or perhaps better, as a kind of pressurized environment which produce, under certain conditions, which produce abelian groups. So let us call crystallographic for a given algebraic structure any categorical setting in which on an object X there is at most one internal algebraic structure of this kind. So according to what we have already said, any pointed Johnson-Tarski variety or any unital category is crystallographic for the structure of commutative monoid. Any strongly unital variety or any strongly unital category, any pointed subtractive variety in the sense of Orsini, or any subtractive category in the sense of Zurab-Zanelidze. And now any CH category is crystallographic for the notion of abelian group. Any Mal'Sef variety or any Mal'Sef category is crystallographic for the structure of commutative and associative Mal'Sef operation. And we can even widen the range of example by saying that in the setting of internal reflexive graph in a Mal'Sef category is crystallographic for the notion of internal groupoid in A.
Dominique, we are running out of time. Please conclude as soon as you can, please.
Okay. So and the first observation is that when there is a duality operator on the algebraic structure, the uniqueness property implies that in a crystallographic context, this algebraic structure is necessarily commutative. And there are some situations which are very surprising. The category AB of abelian group is crystallographic for the structure of abelian group. I shall call not trivial, but minimal crystallographic context. This is also the case for the commutative monoid and the autonomous Mal'Sef operation. So I have to finish now. So a first question about crystallography would be, if an algebraic structure has a non-trivial negative environment, is there a weaker one or an extremal one relatively to some aspect? And more generally, under which condition a given algebraic structure has a minimal or a non-minimal negative environment? So that's the end of my talk.
Thank you, Dominique, for the talk. I hope you can hear the clap here.
Yes, I hope so. It's not very clear, but we shall try.
Thank you. So are there any questions or comments from the room or from the Zoom? There was some clap also on Zoom. I don't think there are questions.
Okay.
I'd like to thank you again for your talk, Dominique. Thank you very much.
Thank you. Thank you.